Okay, welcome everyone for the second session. So for the second session, we will also have three speakers, and I expect a bit more technical than the first session. Sorry. So the speaker we will hear now is Gianluca Bontempi. He's a full professor in the computer science department at the ULB and founder and co-head of the ULB machine learning group. He obtained his master's degree in electronic engineering at the University of Polimi and his PhD degree at the ULB in computer engineering. Moreover, he has been the director of IB Square, the ULB VUB Inter-University Institute of Bioinformatics in Brussels from 2013 to 2017. His main research interests are big data mining, machine learning, bioinformatics, and predictive modeling in engineering and life science applications. So now I will give him the floor for about digital twins for urban mobility.
Thanks a lot for the introduction. Thank you, Emmanuel, Alessandro, for inviting me. So I will give more, as a data scientist, more a data perspective of my vision of smart cities. So for me, a city is smart if it's able to take advantage of the data it produces. So it produces nowadays a city is a complex system, highly complex system, which produces a lot of data. And for me, it becomes smart when it can take advantage of that in the decision making. And seems easy to say, but more complex to do. So I will give a little bit my perspective and my vision on the problem, which is more a digital twin. So digital twin is more really an ambitious long-term objective. And I will try to say why it's interesting from a scientific point of view, from applied point of view. So I will start saying some words about what I mean by digital twin, which is together with smart city. It's a very common buzzword. I would like to convince you that it's not only a buzzword, but it's really a very interesting perspective from research, from science. And then I will say something on what we have been doing in mobility and this ambition to set up a digital twin of mobility. And so we have been mainly working on simulation, and simulation together with data calibration. And then at the end, I will show a little bit the vision that we have for the future. Okay, so when we are talking about digital twin, it means that we would like to have a sort of avatar, digital avatar of something which is real. So every time you are talking about digital twin, you should have on the other side a physical twin. And so the goal of the digital twin is to emulate, explain, anticipate, and control. And if you look at those words, each of them underlies a specific scientific domain. Emulation, simulation, explaining is all the reasoning you can have about the dynamics of a system. Anticipating, it's about forecasting, prediction, control. It's a discipline in itself, decision making. And so what is interesting, in my opinion, in digital twin and a problem like mobility, like smart city, that we have on one side a lot of data, but the other side a lot of knowledge. A lot of knowledge which can be made concrete in terms of models, in terms of physical models, expert-based models, and simulators. And so I think it's a nice domain, nice problem where the two things should be tuned, calibrated, and go together in order to answer the question. So we have an issue of modeling, of simulation, of taking advantage of data, and machine learning nowadays is one of the most conventional techniques to deal with data. And what makes a digital twin different from a simulator or just a model exercise is the fact that we would like to have a continuous two-way flow of data. So it's not just an offline model, offline simulation, but something which should be plugged on reality. And so this could be a sort of vision. On one side, we have the physical object, and then here what the digital twin should ideally do. So we have, first of all, a problem of sensing. So before people mentioned IoT. So nowadays it's possible to create a huge amount of data, but it's not just static data, they are dynamic data. So you have a real data stream, so you have issues of collecting, dealing with streams of large various data. So it's all the issues of big data infrastructure. And then you have issues of pre-processing those data, of modeling those data, and then of integrating those data with existing models. So as I told you, most of the time when you make digital twin of an object or a system, there is a lot of existing knowledge. And machine learning is more proposing a data-driven way of doing, but the two things are complementary, and this requires an effort and scientific research as well. Together with data analysis more for a prediction perspective, you have all an aspect of reasoning interpretability. So when we are talking about a system, we would like to understand what happens if I do something. Okay, so this is related to causal reasoning, understanding among all the variables that you can measure and that you can control, the one which really would have impact on relevant variables. So this is related to causality, this is related to counterfactuals. What if I had done something different? And then once you have created that, you can start playing with that, and playing can be more at the model simulation level or can be more at the forecasting data-driven level. And so this is all the modeling part, but then you don't do modeling only for the sake of that, because you would like to take decisions, and mainly before taking decision, you would like that decision makers play with that. So they start doing some sort of what-if analysis, counterfactual scenarios. So what happens, for instance, in mobility, if a tunnel is closed, and which kind of impact would have on the mobility in the neighborhood. And then this is also, there is a big issue of having an interface between the decision maker and the tool. So you cannot give differential equations to a decision maker to play with. So there are issues of making user interface, of having dashboarding, of having way of representing the strategy you would like to implement. And then ideally, if this strategy is considered to be interesting, closing the loop, actuating, and then all that in principle in the scenario should be done in a closed loop manner. So you see there are a lot of issues, and these, of course, it can be applied to a lot of interesting problems, a lot of interesting domain, from energy to architecture, to climate, to weather, industrial plants. Here Alessandro is doing a lot on combustion plants. And then smart city, last but not least. So from a more research perspective, I think that it becomes a domain extremely interesting, at least for me, from a research perspective, because there is a really convergence of disciplines. It's not only about AI in general, it's about modeling, it's about simulation, and it's about integrating that with data analysis. And so I think that the traffic and mobility is a classical example I will try to show you, where of course we have some sort of scattered in time and space information about the state of the system, but we would like to know much more. We would like indeed to extrapolate, we would like to generalize, because only in that way, and this cannot be done only with a pure machine learning data-driven approach. And so what I find interesting that there should be a synergy between existing models and mobility. They are basically simulators that can be used in order to simulate the dynamics of a city with the flow of data coming from the sensors. And then, as I said before, issues of causal reasoning. You have interesting problems on big data infrastructure, streaming data, and control decision making. So you see, it's a very challenging problem. It's a very challenging problem which requires the convergence of different expertise, which requires a lot of data, and which requires infrastructure. And then this is, we were discussing before about the realism of a smart city. For me, we can reach a smart city environment only if the data infrastructure is made, is implemented, not only for collecting a batch data set, but for having this online interaction with the engine of modeling and the engine of decision making. And I think this is we are quite far from that. So we have, of course, some sensors, we have some data which are collected, but from here to closing the loop, I think is still, there's still a big gap. Okay. And so it's not just a buzzword. Here you have a lot of scientific questions. I think already I presented them, so I can go on. So now we go more we try to apply this idea to the mobility. This project has been basically funded by two initiatives. One, it was an Innovaris project, Torres, which is done in collaboration with VUB and with Mac Electronics, which is the company providing camera to police in Brussels, to Brussels mobility, and which returns information about the counting of traffic in Brussels. And the second project was funded by FARI. Hugo will present FARI afterward. So in this context of FARI, the idea was indeed to interact with public authorities. In this case, it was Bruxelles Mobility and Paradigm. And the idea was indeed to show not only having models for doing prediction, which was mainly the goal of the Torres project, but only having this sort of decision support tool. So now you should realize, when you talk about smart city, that in a complex system like a town, even if you don't make a decision, you are still making a decision. And so in a dynamic system like that, decisions are always taken, and even if they are not taken, they have an impact on reality. And so here we wanted to take a problem where indeed this kind of tool could give a sort of support to the decision maker, and we decided that we wanted to show that this kind of tool could help in the definition of the road deviation when you have roadworks. One of the biggest problems of towns, Brussels and also other towns, that the amount of roadworks which take place every single day is huge. And these roadworks has an impact on the dynamics of the town and requires a reaction, because every time you have a roadworks, you have to make a deviation plan, and this deviation plan has an impact on the mobility. And this deviation plan is basically a control action that you have on the system, for which most of the time people have no idea of the impact. And so the idea of the traffic twin tool was to provide a support on a decision-making process which is made anyway. For the moment, it's mainly done in a manual manner. Of course, based on consultation of different entities, so you can imagine that every time there is a roadworks, there is a lot of actors, from police to local council to other actors which can say a word about that. But there is no way to assess what is the impact of the roadwork and the road deviation on the mobility of the town. And so the idea that, of course, you know about the impact a posteriori, but doing that in a real life settings can be costly, risky. And so the idea was to combine traffic models which were at least a simulator which is based on Sumo, which is an open source traffic simulation, and not only use this as a synthetic generator of traffic, but try to combine that with real data. So the global vision is having a tool which allows people and decision makers to describe road deviation plans and to assess the impact of this road deviation plan on the mobility. And so we had the feeling that this was missing in Brussels region. So this just before that. So was missing because every single day there are hundreds of roadworks which increase the mobility congestion. For the moment, it is just a sort of manual assessment. And the idea was to provide a support, a computer-based support to who is doing that. And so essentially the strategy is a sort of what-if strategy. By having a simulator, you can enter in the simulator what is the roadwork you want to realize, which roads will be blocked, and propose alternative scenarios, so alternative road deviation, and then have sort of qualitative and quantitative assessment for the decision maker. So for the moment, as I told you, most of the deviation plan just defined by domain expert. And so all those decisions for which you see the impact and are not assisted by AI or not assisted by modeling or simulation support. And this is done daily. So daily there is someone taking decision which will have an impact. Of course, most of the roadworks are planned, some of them are not. A typical situation of tunnel which is closed for road maintenance, and these have an impact, and no one is aware of what is the consequence of all that. Okay, so just to give you an idea, so what we developed is a sort of tool which is based on Sumo. Sumo is this simulator, this open source simulator. So the idea that there is somewhat the user will interact with the user interface, and interacting with user interface decide and puts the roadworks on the map. And you can at the same time propose some road deviation plans, and the idea of the tool is to simulating different deviation plan and sort of returning an assessment of that. And of course, this assessment is not a universal assessment. You cannot say this road deviation is better than the other. There is a lot of criteria, a lot of measures which characterize the mobility in a town. And so this is essential, a multivariate problem, and then the only way for supporting someone is proposing a set of criteria and let people decide which criteria is most relevant or most important for them in order to take decision. Okay, just to give an idea, so this is typically the starting point of the level of Brussels mobility. So they basically reason in terms of PDF. They have a PDF saying, okay, there will be a roadwork happening here, and then only on the basis of human expertise and negotiation, because of course you can imagine there is also a lot of political and commercial, financial consideration about the impact of a roadwork on everyday life. They decide how to change the mobility in that region. So basically, we made a sort of definition of what is a deviation plan. So you can formalize that as a set of roads where vehicles cannot drive. You can define a time interval over which you want to assess the deviation plan. You can decide, okay, what is the source road of the deviation plan, the destination road, and all that requires, at the end of the day, a model of the traffic. Okay? So the first tool that we proposed is based only on synthetic models. So we take realistic but synthetic models of the traffic, and we run different deviation plans, and we propose an assessment of that. So if you want to take a look at the demo, Eladio, who is the expert of this tool, is available here. He can interact with you afterward. Here I just show some screenshots. So continuing on the example, this example in Excel, so you see that the idea that the user defines which road is blocked, and then he starts defining a set of characteristic of deviation plans. So what happens if people are coming from the streets, they cannot turn left, so where they're going to go. In the other way around, so you see that in the tool you can insert which roads are blocked and what are the new directions that are proposed. All that, of course, a deviation plan is just not only a single road deviation, but it's a combination of different actions, and these show the complexity of the problem, the multivariate nature, the multi-criterion nature, the stochastic aspect of all that, because all depends on the kind of streets, of the moment of the day, the kind of the amount, the rate of cars or traffic passing by, and so there are a lot of issues to be taken into consideration. And the idea that there is not one, unfortunately, not one roadwork per day, but as you know, there are a lot of them taking place at the same moment. And so this increases, again, the complexity and the difficulty of the problem. So it's quite astonishing thinking that people try to solve this sort of problem, which are extremely complex from a modelization, optimization, multi-criteria perspective, just in a manual, an expert-based manner. But this is done every day, and even if it's not done, it's automatically implemented, because also, as I said before, not doing anything is itself a decision. And so this is basically the idea of the traffic twin tool. So you have this interactive creation of disruptive events. Of course, it could be a planned roadwork, but you could also try to implement events that you don't expect. Okay, for instance, the tunnel or several tunnels that are closed suddenly due to problems like we had recently in Brussels. The definition of alternative what-if scenarios, the simulation of these scenarios, using synthetic traffic models and the quantitative assessment of these scenarios, and then since, as I was telling you, a quantitative assessment is just not one number result, so the idea is to provide an interactive dashboard where indeed the users, decision makers can assess the scenario according to different criteria. And so the idea that in this dashboard we visualize the different traffic attributes obtained with the original configuration, with the active deviation plans, and then by comparing the results of the two simulations, people can have an assessment of the impact of the deviation plan. Okay, so this is just to give an idea of how you can measure the impact of a roadwork on normal mobility, and so there are different quantitative measures in terms of average speed, the time you lose, the waiting time, the edge density, and so it's really a bunch of measures that could be interesting for the decision maker. And so this is basically the kind of graph you can have from the dashboard. So the idea is basically to have a manual assessment but based on simulated data, comparing, for instance, the travel time with and without deviation, average travel time, occupancy with and without deviation, speed with and without deviation. I had another one. Where is it? Okay, no, and there was another possibility of showing which routes, which streets are the most impacted. Because again, when you want to assess that, you would be interesting to know what is the most important consequence of the roadwork on your mobility, and then it's interesting somewhat to rank that. So I think that the role of a tool like that is prioritize the information. Otherwise, you have too much information, and so you should somewhat show which roads are the most affected by the event in order somewhat to have the decision maker to focus on specific part of the area which has been affected. Okay, so this is the first part, but so far, at least in the first version of this tool, we have been using synthetic simulated traffic models, but we shouldn't underestimate that we have a lot, or at least some information about the traffic, and then this information could be used in order to have a better model. And so we can go from simple traffic simulation to a calibration. Okay, so the idea that we had access to counting data over several number of sensors in Brussels, and so the idea was, of course, those are scattered measures in time and space over Brussels, but we would like to take advantage of them in order to have a better simulation model. And here you see the importance of the synergy between a simulation model which is cover spatio-temporally the entire town, and the fact that we have some specific measures in certain position. So this becomes an interesting problem of what is called data simulation, for instance, which is a kind of issue that you can find in a lot of other domains, like in weather, where you have physical models, you have data, and you would like to take the best of both. So now this problem of calibration can be seen as simply a problem of optimization, or problem of machine learning, a problem of estimation, where somewhat you can start from a synthetic model, make simulation, compare the simulation to the observed data, and calibrate the model. And so this is the reason why we are moving from pure traffic simulation to traffic model calibration, as the idea is indeed by having a better calibrated model to have a more accurate way of assessing the impact of events on the streets. So just to give you a flavor of the fact of the intersection between this question and machine learning, so this is kind of techniques which we have been used is a sort of calibration of a simulator on the basis of real data. So essentially the idea is to start with a random solution, so have random trajectories of our vehicles, of our units over the town, and then compare that with the observation. So we have observation in certain sensor, in certain position of the city, and then of course we could have problems of your simulator could not be enough accurate because it's giving too few vehicles with respect to what observed. And then in this case, the idea is just to start creating a set of trajectories over the city, and measuring somewhat the impact of these additional trajectories on the final counting. So we have on one side a simulator where we can have a certain number of trajectories. The trajectories is not only the number of trajectories which matters, but also where they are starting, where they are going. So we are basically a process of exploration in this large solution space. We are creating a lot of trajectories, and we try to minimize the gap existing between what we observe and what we simulate. So this is basically the principle of any optimization or machine learning techniques. So if you have too few vehicles, we increase the number of trajectories. If we have too many vehicles, we start to remove vehicles from the region. And this is the kind of level that Sumo provides you, because it describes the traffic as a set of vehicles going around the town. And so at the end, we go down to the minimization task like that, where Y is the reality, Y hat is the prediction of the simulator. And now what is nice, that somewhat the data allows also to add a sort of machine learning style assessment to the entire process. So since we have a finite number of sensors, the risk, a common risk in machine learning is overfitting. So the fact that, okay, you do very well for those sensors, but you are not able to cover other part of the town. So in that perspective, you can use machine learning strategies, for instance, considering a subset of sensors for training your model, a subset of sensors for testing. And so this, I think it's a nice way of combining the power of data and the knowledge coming from the simulator, because at the same time, the simulator is providing a constraint on the learning. So you cannot learn a traffic model only on the basis of hundreds or thousands of sensors. It will never be enough, because there are constraints related to the topology, to the size of the street, which have to be taken into account, and which are somewhat represented by this Y-hat. So we are not generating model data prediction in a complete non-parametric manner, but what we use the topology, and which is represented by the simulator, and we try to calibrate it. So we search in the space of traffic models which are the closest to the data. Okay. And so again, here you can have a sort of data-driven assessment, just to show, and as usual in this kind of exercise, here you have the error, where we can compare different techniques, different simulator, different calibrator models. So in green, this was the conventional model used by Sumo, and then we have been compared with other techniques, and it's more machine learning way of dealing, of comparing different alternatives, different algorithms, trying to minimize the error. Of course, you have region where the quality is higher, region where quality is less good, but on average, you try to find a good fit. Okay, and then you can reason in terms of training and test and finding a good quality of your model. Here you have other quantitative results about the quality of our model. But so final step, the third thing I would like to say is that now, in any case, what is the added value of not having purely a machine learning predictor, but having a calibrated traffic model, that you can make somewhat augmentation. So now the idea is to predict the traffic not only in the points where you have data, but to predict the traffic also over the other streets. Okay, because most of the time where the roadwork is happening, you don't have the sensor which is available. And so this is the idea of moving from the calibrated model to augmentation, so to provide a sort of virtual sensor. So this kind of simulator can be used to produce the traffic, the simulated traffic based on calibrated model over streets for which you don't have sensors. Here you see the position of the sensor. You see that, of course, they are along the main axis, but there are the smaller roads which are not covered, and of course this requires something which is going beyond pure local and point forecasting. And so the idea is basically to produce value in other place than where it has been collected. So just to give an idea, so what is the basic idea, that you can have a map of your town, you have a step of calibration which is based on real data, and then you could ask, okay, but now give me the prediction, or give me the traffic that is suspected in other streets which are not the one which are observed, and then the idea is to have a sort of additional sensor, virtual sensor. Mobility is a domain where there are a lot of different different inputs which are used. Of course, you could imagine having the counting data proposed coming from the camera of Mac, but you have data coming from Waze, data coming from Google, each with a different frequency, different spatial distribution. So the idea and the most advised manner of proceed is always to make as much as possible data fusion, so take advantage as much as possible of the different sources of information, and we believe that this could be an additional way to provide information for the decision maker. Okay, so this is just basically the final vision. So at the moment we are not closing the loop, since this flow of data, of course we have historical data, we have been collecting 1 year of data, which I think is quite interesting, at least with respect to other results and works in the literature. So we will have the occasion to test on a large scale this model. But of course, we are not closing the loop. We are just, this is a prototype, but in order to close the loop, ideally, of course, it would be nice that this tool is indeed used or adopted to proceed with the decision. So at least as a support to the team which daily is tackling the problem of the road deviation in the town. Okay, so the problem of roadworks will be always there. So this is not the most recent news, but I think 2 days ago we have similar news about the risk of closing of tunnels. So of course all the models are wrong, as I'm used to say. So also this model is wrong, but the idea is to try to make it as useful as possible. Of course, there are additional steps that can be done in order to improve the quality. At the moment, we are mainly counting cars, and we use that as observer of the mobility, but it would be interesting to move to a more multimodal approach. There are always the issues of how the map is really corresponding to the reality. We are at the moment mainly in an offline calibration, while if you start reasoning in a digital twin perspective, online calibration would be useful. There are a lot of additional information coming more from historical and social studies about mobility, but which are most of the time an old, sometimes outdated snapshot on the mobility. So we want to be, as you understood, much more online, real-time perspective. Other directions for the future, introducing additional data sources. You have all the information about the weather events could be integrated, and then the usual issue how to move that from pure prototype, or at least prototype reserves, to something which could have a real impact on the life. So I think that's all on my side.
Thank you very much for your presentation. So, has anyone a question for Professor Bontempi?
Hi.
First,
Yeah. First of all, thank you for your nice presentation. It looks very interesting.
right.
So, I'm a PhD student supervised by Dr. Maida, and we will run some transportation simulation for the whole Brussels capital region, like even larger than Brussels capital region, because as we all know, there are commuting populations in and out the city. And first, I would like to know how large is your prototype is, like what's the scale, the scope?
Okay. So the first version was mainly focused on the commune of Ixelles, on an area, there was the name Tulip area of Ixelles. So it was more a local area, because this was the proposal of the Paradigm partner. But as you have seen, now we are more considering Brussels level, so the entire Brussels region level. Of course, there is always in a representation like that an issue of how to address the input and the output, so the inflow and the outflow of this region. I don't know, Eladio, in terms of largest size of the map, we could manage something comparable to region of Brussels.
In this case, it's just the region of Brussels will be the
But I
that's-
mean, it depends a lot on the kind of data we have, the kind of resolution,
Exactly, yeah.
granularity you want to attack. I didn't mention, but in a very interesting source of data we have been working in the past is all the track data, the BrIAS. Probably this is one of the most interesting real time that we had access a long time ago to those data. Now it's much more difficult to have them, but this is again another interesting source of information, more at Belgian level, that can return insight about the traffic more general.
Yeah,
level.
indeed, sounds very convincing. And the second question would be, what's the spatial resolution? Because our collaborator in EPFL Switzerland also runs some simulation in a 500-meter grid. So they try to find develop the OD matrix between this grid. And you also show something in the map. I would like to know what's your spatial resolution.
So we are still also considering OD approaches. For the moment, it's more our model is a set of trajectories which are all over the region of interest. Now, the approach we are taking is really a data-driven approach. So the only information about the reality is the set of counting over a set of sensors. So what we want is to have a realistic fitting of those data, spatial-temporal data. And so this is basically our cost function. Of course, there is a constraint, so we are not generating all sorts of models, but these models should be somewhat compatible with the topology. So we are considering only the models which can be generated with Sumo. So we somewhat searching in the space of traffic models that can be generated by Sumo, try to mapping them to the data. Of course, there is different issues when you assess the quality, so you can do at a global level, or you can do a sort of, in order to avoid of having, since at the end we are addressing the average error, you would like to avoid that you have a very good error in one region, very bad, but on average is good. And so this is sort of granularity. This is, for instance, I think it was Namur. We have a set of local region where we have a check about the local quality, which is a smaller size. And so there is for sure an issue of granularity in this term of assessment, because this has an impact on the cost function and then on the quality of the model. But this is still, open issues. And OD, of course, is a very nice possibility, but who is going to provide us some good OD matrices? So this is the issue. So most of the time people make a lot of assumptions about the patterns of traffic, which are relying on survey, but how is it realistic? And we would like to have much more real-time accuracy.
Yeah, we also asked the SPRDB Brussels for help, but they have a model called MUSTI that runs some simulation about the metropolitan, but so far we cannot get anything from them. Yeah.
Yeah.
And the third question would be, like you mentioned some truck and vehicles, but you probably know, like we focus on soft mobility, the pedestrian. Do you have any data?
Not yet. In the future, we would like to integrate that. But in any case, the best is if you talk to those guys, to Eladio, to Alejandro, for details. But yeah, we are not yet integrating bike data, but yeah, we are planning to do in the future. Yeah.
Thank you for the presentation. Just a quick question regarding, like in your experience, the people that work like now manually are trying to understand this kind of deviation or the traffic flow. Are they eager to use this kind of models, or they're a bit skeptical about the machine learning part?
No, the idea, I don't think this kind of tool should close the loop and provide a solution magically. Also because deciding, it's a really multi-criteria problem. Even if I show you 10 figures over 10 criteria, is up to the human to say, okay, what at the end of the day is the most important. So I think in principle they are always eager. The problem is they really enter the process, and who is really motivated in having this tool and entering the process. This is more, I think, human work organization issue that in principle they are not against, because I don't believe on the fact that we could automatically select the best road deviation plan. I think it's too complex. There are too many criterion. But just showing, okay, if you do that, this is doing better, this is doing worse. The idea could be an additional input to the final decision making. This is what we are targeting to. But again, in entering this process requires resources. So it's not simply something that, so it requires a sort of resources for bridging the gap between what we are doing, what they are doing daily. So I think Hugo will say something about these eternal issues of how indeed to transfer this kind of results to the real world for public good, how to make it real.
Thank you.
So the parameter you would focus on, if it's mainly if you're concerned about economical part or social life or whatever the part.
I think as a scientist we have to make models and make a prediction and propose scenarios. I think it's the role of politicians to put the weight on the scenarios and take the decision. As simple as that. So it's really going. So of course, if you make an automatic choice, automatically you're assuming that some costs are more or less important than the others. So I think in such a sensitive domain, we have seen with good move, it's going beyond mobility. It's more, I think it's more political sensibility, which is at stake. So I don't think we cannot, in that case, they would be very skeptical, but I don't think this should be our claim. Our claim should simply, you have an additional tool where you can do what in any case you do, you make a mental assessment of choices. Here you have an additional support. And then, of course, the decision is up to you. But now you rely on a set of criteria, of numbers, which is richer, or graphical information, which is richer than what you could simply imagine.
Yes, so my question is, do you mean that it is not possible to anticipate the traffic deviation based on the quality of the streets, for instance?
So you mean automatically optimize finding the best road deviation? What you mean? What we are doing is basically that. We try to anticipate by simulation, by using a calibrated model. We are making the forecasting, the prediction of the impact of the road deviation. So we are producing number which are, it's a what-if scenario. So if you block the road there, and if you trust the model we made, this is what could happen. Okay. But again, it could happen as a lot of implication at different levels, different variables, and so then it's up to humans. If prefers to have a congestion in road A instead of road B, you prefer to keep a low speed. So there are a lot of different criteria. Then, so what I'm claiming that it would be hard to find the optimal. But it would be somewhat a bit stupid not to take in consideration the opportunity of technology in providing assessment of scenarios. So I think this should be a support to the decision.
Okay. Well, yeah. Thank you very much.
You're welcome. Thank you again.